So yeah, today I want to talk about this notion of wobbly and its counterpart, very stable Higgs bundles. But specifically for today's talk, I want to focus in the setting of parabolic Higgs bundles, okay? So this is a notion that kind of appears in the context of mirror symmetry for these moduli spaces. And so what I want to do first is I want to give an overview of the context of, without defining anything, I will just give the context of mirror symmetry for moduli spaces of Higgs bundles, and then why might we care about the parabolic setting? And then after that, I will state the problem that I want to actually look at, and then I will define everything. So. Okay, so as I was saying, this is in the context of mirror symmetry for moduli spaces of Higgs bundles. And for the problem that I care about, it will be in precisely in the moduli of strongly parabolic G-Higgs bundles, okay? But first of all, let me review the context of mirror symmetry aspects that appear in moduli spaces of usual Higgs bundles, not necessarily parabolic, okay? All right, so as we know, we have this moduli space, which is a quasi-projective variety, and it has this hyperkähler metric. It's a hyperkähler variety. And in particular, so it has these three complex structures satisfying the quaternion relations, and several as well symplectic structures. And I'm going to fix this omega to be the holomorphic symplectic form, meaning the holomorphic with respect to the complex structure that comes from the Higgs bundle interpretation, not the Atiyah bot that appear in other talks. Okay. So now, because it turns out that this whole mirror symmetry story for moduli spaces of Higgs bundles comes from, I guess, this initial observation of Hausel and Thaddeus, which was that these moduli spaces fit into the picture of mirror symmetry, which is this physical duality that should relate two different Calabi-Yau manifolds and should somehow interchange the physics in both sides, the symplectic geometry theories in one side with the complex geometry in the other side. So how this is mathematically realized, there are several different statements of mirror symmetry for Higgs bundles. One of them is the duality of the integrable system. So here on the left, I have the Hitchin integrable system from the moduli space to this affine space, this vector space on the base. And this is, as we know, this is a completely integrable system with proper fibers, and generically we have these abelian fibers. And then the one statement about duality for these moduli spaces is a duality of these abelian fibrations, this SYC mirror symmetry. So this basically states that for this Hitchin system, which is an abelian fibration, there is a dual one, which turns out to be another Hitchin system for a different structure group, which is the Langlands dual group of our starting group. And what we mean by dual fibrations is that the bases are identified, and these generic fibers, which are abelian varieties, are dual abelian varieties. Okay. And in the work of Donaghy and Pantev, they prove this over, this duality of the generic fibers. Now, also at the level of sheaves, we should expect some dualities because, at least from the physics, there is this physical principle where the symplectic theories under boundary conditions, which can be expressed with sheaves, the so-called A branes, should be interchanged with the boundary conditions for the theories with complex geometry, the B models, which are called B branes, okay? So there should be some dualities at the level of sheaves. And I'm going to care about, for the motivation, I'm caring about this classical limit, which is the equivalence on derived categories of coherent sheaves on both sides. Okay? And in the work of Donaghy and Pantev, they actually prove this over the generic locus of the Hitchin base using the geometric picture that we had before. So they, over a generic point in the base, we have dual fibers, and so you can perform a Fourier-Mukai transform along these fibers, and you prove this equivalence over that generic locus. Okay. Now, there is this work of Kapustin and Witten where they relate this mirror symmetry for Higgs bundles. They explain it as some kind of S-duality for some quantum field theories, and also they relate it to the geometric Langlands program. But then they also consider the whole hyperkähler package, not just the A branes and the B branes, but they consider each of the 3 different structures that we have. And so depending on whether it's a brane for either the symplectic part or the complex part, we can speak about stuff like about things like PAA branes, which means a B brane with respect to the first structure and A with respect to the other. We actually saw this on Tuesday on Professor Hitchens' talk. Yeah, so these PAA branes, roughly speaking, should be, you take a holomorphic Lagrangian with respect to the holomorphic form that I mentioned before, and then there should be local systems on those things. And then BBB branes are these hyperholomorphic connections on hyperholomorphic subvarieties. And so this notion of very stable and wobbly that I'm trying to get to comes from the problem of studying examples of these things, okay? Because we're in the moduli space of Higgs bundles. There are not many examples of these BAA and even less for the BBB as we saw on Tuesday. But one kind of manageable example that one can construct using these upward flows that are obtained using the C star action on the moduli space. As I say, I will define everything later. So if you consider natural scaling action on the moduli space, then you can consider the Bialynskii-Virula upward flows. And these will actually define examples of holomorphic Lagrangian submanifolds. And so they are candidates for BAA branes, which have a simple geometry. And then among those, so this motivated in this work of Hausen and Hitchin, it motivated the introduction of the notion of a very stable Higgs bundle, which roughly means that these BAA branes are the simplest possible in the sense that they are closed and they intersect the Hitchin fibers in a nice way. We will see the definition later. Okay. So this is what I care about for this presentation. It's actually describing which of the Higgs bundles are very stable, but in the setting of parabolic Higgs bundle. So why could we care about parabolic Higgs bundle in this context? Well, if we try to think about what happens with parabolic Higgs bundles, in this case, the moduli space is actually a Poisson variety. So we don't have these symplectic structures, but we can restrict to each of the symplectic leaves and try to ask whether the same questions make sense. And so what we will do is restrict to the symplectic leaf of strongly parabolic Higgs bundles, which we will define later. So yeah, this is kind of maybe the easiest in the sense that the previous picture and the integrable system for the strongly parabolic moduli space, it's kind of the most similar to the usual moduli space. Okay, so apparently there are some stories for mirror symmetry here, which are initially introduced or described in the physics in this paper of Gukov and Witten, where they apparently, I'm not too familiar with the physics, but apparently the parabolic puncture should correspond to some kind of surface defects on the quantum field theories. And then they should also relate to the ramified Langlands program. And so there should be some kind of mirror symmetry story for these spaces. And I could find some examples in the literature where we take where in these examples that I found in the literature, the dual of the moduli space of strongly parabolic for some weight is actually, again, you take the Langlands dual and some dual weight. And so these examples are, I listed here. So for example, there is topological mirror symmetry, which I didn't mention before, but it's the agreement of some topological invariants, some kind of version of the Hodge numbers. And this was shown for SL2 and SL3 in this paper by Gother and Oliveira, and later generalized to arbitrary rank independently by 2 different groups. One of them is Su, Wang Wen, and the other Shen, using some recent techniques that were developed to prove topological mirror symmetry even in the non-parabolic case in this work of Gechenig, Wies, and Ziegler. Okay. And then I also found this reference by Biswas and Day where they show the SYC picture for SLN. Okay, and I also think there are more recent works of this team of 3 people above, which work with the type B and type C duality in the SYC context. Okay, so there is kind of a similar story of mirror symmetry in these moduli spaces, and so my goal is going to be study this upward flow problem and this notion of very stable or wobbly Higgs bundles in this context, okay? And this will then open the possibility of trying to test the mirror brains. Okay, but here we will just focus on the sister action. Okay. Right. Okay. So this was yeah, sure.
So I just want to understand. So your motivation is to study mirror symmetry in this hyperkähler context, right?
Yes.
And you mentioned homological mirror symmetry as a motivation. But one thing that's always confused me is in this context, there doesn't seem to be a notion of morphisms or like open string states stretching between branes, because branes are boundary conditions.
Yes.
So I don't understand what the statement, what kind of statement one is hoping for.
Yeah,
I'm the mirror sides.
Yeah, right. So I'm just kind of giving the overview, the sort of general picture, and I don't know if the homological mirror symmetry is well defined in this case, but I'm just looking at this classical limit version somehow, which is in,
what kind of statement is one hoping for in this context for BAA branes? I understand that one doesn't yet have the homological setup, but is there some,
yes,
some shadow of that one?
Yeah, the shadow should be, the shadow should just be that these equivalence of categories that we have with sheaves. If we take a sheaf representing a BAA brane, which for me mathematically is just these local systems, then we apply this should land in a sheaf representing a PPP brane. But yeah, that's, yeah. Okay. So, okay, so let me define the objects that I will work with. So my structure group is going to be connected and semi-simple complex group. And I denote, I take the Lie algebra. Then I will fix some Lie theory data that I will need. So I fix a maximal torus and a Borel. They're Lie algebras. And this choice determines some simple roots that I denote with these betas. Okay, so I will work over a smooth projective complex curve, and the canonical line bundle I denote by KC, as usual. And then for the parabolic data, I will fix as punctures on the curve. And then at each puncture, I will fix a parabolic weight. So a parabolic weight for me is an element of the Lie algebra of the torus. And then this R means that I want it to pair with the roots in real numbers. Okay, so it's the Cartan subalgebra for the split real form of G. Okay. And then I will make an assumption on the weights that will simplify the definitions. So yeah, for this talk, so the weights I'm going to pick in the interior of the standard Weil alcove. So this is just a condition that requires them to be in a bounded region, an open bounded region, which is given by this inequality. So when I pair with a simple root, this needs to be positive, and when I pair with the highest root, this needs to be at most 1. But in principle, what I'm going to tell you would work for any choice of weights. But the definitions and the moduli spaces that one would need to consider are more complicated, and one would need to work with parahoric moduli spaces, but it would still be possible. Okay, so then what is a parabolic Higgs bundle? It's well, 3 things, 2 of which we are already used to from the other talks. We have a principal G bundle over C, and then the Higgs field is a section of the adjoint bundle twisted by the canonical and then twisted by the divisor D. And then the other thing are the parabolic structures, which are just a choice of Borel orbits in our fibers over the punctures. Okay, so at each puncture, we choose an element of this quotient. Now, this choice of a parabolic structure is the same as choosing a Borel subgroup on the adjoint bundle for the group. And so it gives us a Borel subalgebra of the adjoint bundle for the Lie algebra. Okay. And then we are going to ask a comparability condition our Higgs field with the parabolic structures, which we can state simply as follows, that the Higgs field at the punctures should be contained in this Borel subalgebra. Okay. And then, as I said, I will focus on the case of strongly parabolic Higgs bundles. So this, in this context, can be stated as whenever I look at the Higgs field at each puncture, this has to be nilpotent. Okay. Great. So that's the definition. And from now on, I will stick to this strongly parabolic. So I want to give later like an easy example where we can see what's going on, and that will happen in PGLN and actually in PGL2. So in case you prefer vector bundles, here's what happens for PGLN. So your PGLN bundle you can interpret as you can see as a Rankine vector bundle up to twisting by a line bundle. Then the weights, which are not going to play a huge role in what I'm going to tell, but the weights, we think about the Cartan subalgebra as diagonal matrices, then we just have to specify in real numbers. And then because we are in PGLN, they need to sum to 0. And then all these inequalities are these standard Weil-Alkov condition that I mentioned before. Now, because the parabolic, the Borel is the stabilizer of a full flag, then the parabolic structure is just a full flag on the fiber. At each parabolic puncture, I just choose a full flag. And then the Higgs field is a morphism of vector bundles from an endomorphism of the vector bundle twisted by the canonical and the divisor. And the compatibility condition with the flag in the strongly parabolic case is that each step of the flag is sent to the previous one. Okay. All right, so as I said, this notion of very stable and wobbly relates to this C-star action on that we have on the moduli space, which is just scaling the Higgs field by a complex number. And now, even if the moduli space is not projective, it's just quasi-projective, but we can take the limit when our C-star action goes to 0, and this will contract the moduli space into the fixed point locus, which is actually proper. So this is why we say that this action is semi-projective. We can always take limit when lambda goes to 0. And therefore, we can have a Bialynskii-Birula stratification where we stratify, for example, the smooth locus. We stratify depending on the fixed point component that we hit for each point. And then if we take an individual fixed point, we just choose a fixed point of this C-star action, and then we consider the upward flow or the attractor cell, which is the points in our moduli space whose limit is this fixed point. Okay, and this defines a subvariety, and this is one of these holomorphic Lagrangians that I was mentioning in the context. Whenever the fixed point is smooth. Okay. And the geometry of this is kind of simple. These are isomorphic to just affine spaces on the moduli space. But the caveat is that they could be not closed Lagrangians. So let me now move into the definition of a very stable Higgs bundle and what does it mean. And it's basically analyzing two different possibilities that can happen for these upward flows, which I've sketched in these pictures. It's rough, very rough. So here in the pictures, these kind of blue lines here and the fixed point represent the upward flow of the point over the Hitchin base. So the Hitchin base is this line. And then this is supposed to represent the Hitchin system. And then there are two possibilities, evidently, when looking at the nilpotent cone, which is the fiber over 0, which is where our fixed point lies. The first possibility, the simplest case, is when on the nilpotent cone, we just have the fixed point itself. And then all the other points in the upward flow, if we take lambda going to infinity, they will just grow unboundedly, as we saw, for example, in the previous talk. And therefore, what you get is a closed subvariety. And the ICMAT then restricts to a finite cover of the ramified but finite cover on the upward flow. So this is what, in this case, we say that the fixed point, which we, from the beginning, we assume is a smooth fixed point. In this case, we say that it's very stable. Okay. And then the other possibility is that you have more things in an nilpotent cone. And then in that case, when you take the limit in the other direction, when lambda goes to infinity, they will not grow unboundedly. They will hit another fixed point, this white circle in the top. Well, or there could be different directions hitting different fixed points. And so the upward flow in that case is not closed. And of course, it's not a finite cover. And we say in that case that the fixed point is wobbly. Because this terminology, by the way, comes from the classical terminology of a very stable bundle introduced by Drinfeld and Lomont. Okay. And so in that case, it will go to another fixed point. And if we want to get a closed thing, then we will have to, or a closed Lagrangian, we will have to add the upward flow for that point and keep doing that. And then the geometry of the whole thing will become much more complicated than in the very stable case. So are there any questions about the definition of very stable? Yeah. That's a good question. I think generically, if I recall correctly, in the work of Hausel and Hitchin, generically over the base, they compute the number of points, and it's a finite number. But I'm honestly, I'm not sure about what happens in all the fibers. Yes. But the distinction is on the fiber over 0. Yeah. Okay. Right, so then the goal for what I want to do for the remainder of the talk is try to investigate what happens and try to reach a classification theorem for these very stable, or at least a certain class of very stable fixed points. But in order to do that, I want to try to get some intuition by working in a simple case, which is basically the simplest setup I could think of is you take PGL2, and then you take a single puncture. And then you take a non-negative integer, which will represent the vanishing of the Higgs field. And then I'm going to give you a family of fixed points of the sister action, and we are going to think whether they are very stable or not. So for my vector bundle, I will take these similar things have appeared in other talks. I'm going to take a direct sum of 2 line bundles. First, the trivial bundle, and then the anti-canonical twisted by k minus 1 times c. And for the Higgs field, I just take it to be if we write it in this form with respect to the decomposition, I would take it to be nilpotent with just an entry over there. And this entry has to be a section of this second factor twisted by kc and twisted by c. So it needs to be a section with divisor k times c. So it's a section with vanishing order k at the point c, which is what this represents. Okay, and then I have to give the parabolic structure, but before that, let's think why this could be a fixed point. And indeed, if I just scale one of these 2 summands, for example, the trivial line bundle, I apply the automorphism of scaling by lambda to the -1, for example, then this will take the Higgs field to lambda times the Higgs field. So it seems like it could be a fixed point, but then the parabolic structure that we need to put needs to be fixed. So the line that we choose on the fiber needs to be fixed by this operation. So there are not many possibilities if you think about it. One of them is we just take the second factor, which I call the tail. This is just the flag that goes from the tail and adds one of the pieces at a time. And this is fixed by this scaling of the first factor. So this will give a fixed point. And then the other option is start from the beginning and take as a line the first component. And when you scale this component, it preserves the line. However, there is a compatibility condition with the Higgs field. In this first case, there is no problem. because indeed, if you look at the Higgs field, this is mapped here and this is mapped there. But in the second case, in general, it's not true only whenever the section vanishes. So if the vanishing multiplicity is positive, then at the puncture we have the 0 Higgs field, and so we could put any flag, and these two will give fixed points. Okay. So now I want to think which of these would be very stable and which of these would be wobbly. And the main insight, which already appeared in the non-parabolic setting in the work of Hausel and Hitchin, is that for fixed points of this form, everything can be described using Hecke transformation, so modifying your fixed point locally around a given point. So indeed, I mean, certainly when you take a parabolic or a Higgs bundle and you modify it around a point, this will remain in the same Hitchin fiber, so it will remain in the nilpotent cone. And then if you manage to do that so that it moves along the direction of the upward flow, then you can, if you can do that, you could prove that your, according to the previous picture, you would prove that your fixed point is wobbly, right? And the insight of Hausel and Hitchin is that for fixed points of this form, and I will be more precise what this form means, but in these examples, everything can be understood by just looking at these local transformations. So anyway, so then what happens with our examples? So if I have k equals 0, then, I mean, one way to modify a parabolic Higgs bundle locally is to just modify the flag. So the first thing one should look at is what are the compatible flags? And in the case where, if you remember, in the case where k equals 0, meaning that this doesn't vanish, there is only one compatible flag, which is this tail flag. So we cannot modify the flag. And then the next thing we have to ask is, can we modify the bundle? Can we do a Hecke transformation of the bundle itself? And it turns out that because if you want to do that in the direction of the upward flow, you would need to introduce poles on the Higgs bundle because there is not enough vanishing here. This is roughly the intuition. Therefore, this will be very stable. Okay, I just gave you a kind of idea. This is not the rigorous proof. And actually, an easy way to see that this is very stable is just considering the Hitchin section for this, the Hitchin section for this parabolic moduli space is, in this case, it turns out to be precisely the upward flow of this point, and therefore it is a section. It is a finite cover. It's a section. Okay, but there is a little bit something more interesting when we have vanishing on the Higgs field. So here, this vanishes. Then we could choose any line to be the parabolic structure. We saw in the previous slide that these two lines give you fixed points, but if we don't care about fixed points anymore, we could choose any line that we want. So for this parameter in P1, we could take the line with coordinates t, 1 in this decomposition. And this will give you a parabolic Higgs bundle. And now, because you have this freedom, you can just look at modifying the flag. And if you remember, when we scale this trivial bundle by lambda minus 1, the Higgs field gets scaled by lambda. And so looking at this, also this QT line gets scaled by lambda minus 1. So what this means is that actually, if I apply the C-star action to this point, this is the same as just scaling the parameter in P1. So we get an induced C-star action in the space of parabolic structure. And then, of course, if we take this family that we have constructed, then the limit at 0 will be wobbly because we have constructed this whole family without even touching the bundle. So in this case, where the vanishing is greater than 0, because we have so many compatible parabolic structures, the limiting one at 0 is going to be wobbly. Right. So now we could ask, is there any other very stable point? If we want another very stable point, we need to put the flag at infinity, which is the head flag. And then we need to look at the modifications of the bundle, at the local modifications of the bundle at either at the parabolic puncture or at another puncture, another point in the curve. And so it turns out that because of this phenomenon that I was talking about with the poles and so on, you need, if you have enough vanishing multiplicity, you can create a family. I will be more concrete later. But if the only situation where you cannot do that, and therefore you get a very stable thing, is for the vanishing multiplicity 1. Okay? So kind of the intuition that I wanted to show with this example is that you need to look, so this behavior is going to be governed by both the parabolic structures that we have at the punctures and then the vanishing multiplicities that we have at the Higgs field. And so if we try to do the same for PGLN, and at this point is where I introduce this assumption that the fixed point has a generically regular nilpotent Higgs field. This is the class of fixed points that I will work with, so that then they look similar to the example. So the reason for this assumption, by the way, is that in that situation is where everything can be understood via Hecke transformations or via local modifications of the bundle. And then, well, with that assumption, the fixed points will look like this. Okay, just a direct sum of n line bundles, and then the Higgs field is given by n-1 sections of line bundles with vanishing divisors di's, these di's that appear on top. So again, this is fixed because I can scale each summand by a power of lambda, and this scales the Higgs field by lambda. And this induces, once again, as exactly as in the previous example, a C-star action on the flag variety. And then the flags for the fixed point need to be fixed under this C-star action. So you might imagine that it's similar to what we saw before, in the sense that the only fixed flags are those which respect this grading. So we just have to take one piece at a time in whichever order. Then it has to be compatible with the Higgs field, which that of course will depend on the vanishing. And in any case, we will always have the tail flag compatible with this Higgs field, but then the other flags will depend on the individual vanishing of these sections, as we will explain more precisely. Okay, and then the intuition is that this should be very stable if the vanishing is low enough and if the parabolic structures don't have this kind of upward flows in the flag variety. So this is what we expect. There should be a condition on the vanishing, which I will explain why this one in a second. So the sum of these divisors being reduced. And then some condition that we will see in the statement on the theorem about the flags, the parabolic structures, okay? And basically the condition is on the flags is that we want that under this C-star action, the upward flows of these flags are points, basically. So we cannot deform them anymore in the upward flow. So this first condition is the one studied by Hausen and Hitchin. Basically, they studied the Hecke transformations for these kind of vector bundles, and they concluded that whenever you have this condition, you cannot do Hecke modifications in the upward flow. So this is just, we will see in the theorem that this is actually correct, but for the expectation, it's just taking the same condition. And then there is this related work of Tim Henke in his PhD thesis, where he actually, for GLN, he writes down this minimality condition. His condition is essentially you take the tail flag, which is the one that, remember that this tail flag is the one where you just take each line from right to left in the fiber. And then you take this tail flag, which is always compatible, and then you swap it around in the sense that you take the one that is as opposite as possible to this tail flag while being compatible with the Higgs field. So we will also make this a bit more precise in a second. Yeah. Okay, so now I want to go towards the statement of the classification theorem, which, remember, we want to determine when a fixed point with generically regular, we assume, generically regular Higgs field is very stable or wobbly. Okay. So, yeah, so I will focus on this. Generically, the Higgs field is going to be a regular nilpotent element on the Lie algebra. Then I will set G1 here, the sum of the simple root spaces. And then, remember that the Weil group of the group is this finite reflection group obtained like this, the normalizer of the torus over the torus. And then for later, I will also need this dual basis to the simple roots, which is the fundamental co-weight basis, okay? Anyways. All right, so first, what are the fixed points? What do the fixed points with generically regular Higgs field look like? They have to satisfy 3 conditions. The first 2 of them are actually, they appeared in the talk of Jochen this morning. We need a reduction to the maximal torus, which would be the G0 that appeared in his talk. So what I'm trying to state here is if we have a parabolic Higgs bundle in our moduli space, it will be a fixed point with generically regular Higgs field if and only if there is some reduction to the torus such that the Higgs field takes values in this G1, this sum of simple root spaces, which correspond to this graded piece under this principal co-character. And then there is a condition on the parabolic structures. So because we have a reduction to the maximal torus, one could ask, or one could think, this condition is that the parabolic structure comes from a parabolic structure in the reduction, but of course, then you think about it and well, if we have a T bundle, then the parabolic structures at one point, there's just one possible parabolic structure. So one needs to introduce this action on the Weil group. So for the parabolic structure to be fixed, what I'm writing here is you take the space of parabolic structures on the reduction, which in this case is just a point because it's a T bundle mod T. So this embeds naturally in the space of parabolic structures on your G bundle. And then you take the Weil group orbit of that. And this is the correct condition. And of course, I wrote this in this funny way because you could describe any, this is for a generically regular, but if we replace the maximal torus by any other levy of any other parabolic, and we replace this G1 by the corresponding graded piece. And then here we do this same procedure, but instead of the maximal torus, you put this levy. And then you need to keep the action of the Weil group. Then that describes fixed points in general. But generically regular case is this one. And also, yeah, if you took, instead of T, another levy, then here you could quotient out by the Weil group of the levy, which would act trivially. Okay. Okay, so now we have this description of the fixed points. And now with this description, we can extract the data that we care about, which is the vanishing of the Higgs field and the parabolic structures. So for the vanishing, it's very easy. We have because the maximal torus acts on every root space, we project to each of the simple root spaces. And then we get these components. In the PGLN example, we saw that we had this phi1 to phi n minus 1 on the diagonal, 1 per simple root. And then these are sections of line bundles, and you can ask about their vanishing. And then at the parabolic punctures, you have the parabolic structure, which, as we saw in the previous statement, it should be contained in the Weil group orbit of the parabolic structure of the reduction, which is abstractly identified with just the Weil group, because this is a point. And so I will denote by this U at CI. This is supposed to represent the Weil group element that corresponds to our parabolic structure. Okay, and then it turns out that there is a natural way to collect all of these, which I will stop now to define, which is, okay, this twisted multiplicity divisor, which just collects all of this data at each point. So basically, at each point in the curve, for each point, I have a divisor, but then the coefficient is not an integer. Then the coefficient records both the multiplicity or the vanishing multiplicity of the Higgs field, which is this part. So we take this means the vanishing of each of these components at the point C. And then we make it into a linear combination of the fundamental co-weights to get a co-weight of the Lie algebra. And then we multiply that by the Weil group element. And so the group where this information lives in, and it actually naturally lives in, is in this product then. It's the product of this P check, which is the co-weight lattice of the Lie algebra, with the Weil group. And this is this extended affine Weil group. And we will see why it's natural to consider this group in a second. And then I just want to point out that if we are not in a parabolic puncture, then we don't have this Weil group component. And then it's more natural to just think of it as a co-weight. We just have this part, and in fact, anti-dominant co-weight because of this sign. And then it's natural to think about this anti-dominant co-weight lattice as this double quotient of the extended affine Weil group by the Weil group on both sides. And the reason for that is I mentioned that I'm taking the weight in the interior of the Weil alcove for simplicity, but if you take the weight somewhere else, then you will get different double quotients in between or related double quotients of the extended affine Weil group. Okay, so then in this, what we saw in the example and in the expectation, we expect a minimality condition for the vanishing and for the parabolic structures. And it turns out that now, under this perspective, we have the extended affine Weil group, which has a natural notion of minimality, which is just considering the natural order, just a natural ordering in this extended affine Weil group, which is a partial ordering known as this Bruhat order. And this comes from the fact that up to finite index, this is a reflection group. So as with the Weil group, you can define a length function and an ordering. And it turns out that this, if we take this point of view here, this ordering is actually what is governing the structure of the upward flows. And in particular, the very stable elements are going to correspond to the minimal elements under this ordering. Okay. So then, if you don't know this ordering, it's fine, but maybe you just want a concrete condition in terms of the vanishing and in terms of the parabolic structures. So let me quickly describe what are the minimal elements. So if I take a co-weight representing the vanishing and I take the Weil group element representing the parabolic structure, what is the minimality condition? And then the condition is the vanishing part, so the co-weight part has to be minuscule, meaning that, well, there's the definition, meaning that when I pair with any positive root, I get 0 or -1. So actually, what does this mean for us? This means that we can have at most a simple pole on our Higgs field along one of the simple roots, but not any simple root, only those simple roots which appear with coefficient 1 in the highest root. So basically, it's you can only vanish at certain simple roots and only one of them. Yeah. And then the condition for the parabolic structure, so here there's a long kind of paragraph, but what I mean is you take the space of parabolic structures comparable with your Higgs field, okay? This will give you a space of parabolic structures, and that space itself will have a Bruhat order, which is just the restriction of the Bruhat order of the usual Weil group. And then you take the maximum, which is unique. So you take the longest element in that set. So this is what it means, that the element as opposite as possible from the tail flag. The tail parabolic structure is the identity in the Weil group. And so this is what it means. So then this set of comparable, so what I'm writing here is that this set of comparable parabolic structures is this minimum length representatives of this quotient by the stabilizer of the vanishing of mu. But yeah, just the space of comparable parabolic structures. Okay, so now Yeah, so now basically I can state the theorem which is as you expect. So I'm telling you that this Bruhat order is governing the ordering on the upward flows. So what we want, the minimality condition, is we want that all of the coefficients of this divisor, so all of these extended affine Weil group elements at each point need to be minimal. And minimal here means in the parabolic points, this condition. And then outside of the parabolic points, we actually think of it as this double quotient from before, and then the condition on U disappears. It's just the minuscule condition. And when that happens, let's say that our divisor is reduced. But anyways, so the result is that you take your smooth fixed point with generically regular nilpotent Higgs field. You extract this divisor, which is just recording the vanishing and the parabolic structures. And then it will be very stable if and only if the divisor is reduced. So if we have minimality at each point. Okay. And so this recovers previous results. In particular, all that I told you works if there is no parabolic punctures, which is some previous work that we did. And in particular, there is this result also for GLN of Hausel and Hitchen that is sort of generalized in this way. Okay. Okay, so now I want to finish by sketching very briefly the proof, because I put in the title these affine flag varieties. So, I should talk about them. So the strategy is going to be the following. So this is the same strategy that I mentioned in the example. We look at the local modifications of our fixed point at each puncture. So if we just ask what are the Hecke transformations of our parabolic fixed point at a given parabolic puncture, this is parametrized by this affine flag variety, which is the loop group, the puncture disks on our group G, mod the Iwahori subgroup, which is the disks on our group, which at the center of the disk land in the Borel. And then when we have a Higgs field, because what I mentioned in the example, if there is not enough vanishing, the Hecke transformation could add poles to the Higgs field, or it could make it not compatible with the flag anymore. So you have to restrict to this to this subvariety of to this subspace of the affine flag variety, which is defined by your Higgs field, and it's essentially the subspace of those transformations that such that when you transform the Higgs field, you get a well-defined parabolic Higgs bundle. Okay, and then the key point is that this space, this affine Springer fiber, has an induced C-star action, which is intertwined with the C-star action in the moduli space, meaning that if I do a transformation by one element here and then apply the C-star action, this will be isomorphic to applying the C-star action and then applying the transformation. Yeah, so this is what I mentioned. So then, so this space over here records our possible Hecke transformations. And when we apply them to the fixed point, we get something which is still in the nilpotent cone, because it's just a local transformation. But now we need to look at the directions which live in the upward flow. And that will be exactly the upward flow of the identity element in the affine flag variety, where here I mean the upward flow under this induced C-star action. Okay. And then because of this intertwining property, this will land in the upward flow directions on the nilpotent cone. Okay, so then basically what I'm trying to say is that we just look at the space of Hecke transformations, and then we reduce the problem to a local problem, and then we just study this. So this is, yeah, whenever we have a minimal coefficient, a minimal element in the extended affine Weil group, this upward flow will just be a point. And then otherwise, one can prove that this contains a curve of transformations, and therefore this will translate into a curve in the upward flow in the nilpotent cone. Okay. And then, yeah, I didn't mention stability throughout the talk, but of course, it's important to consider whether this stays in the moduli space. I mean, we're starting with a smooth point, so it turns out that you can prove that when you start in a smooth point, which in particular is stable, and then you apply this, well, of course, the curve will be stable, but then also you can prove that the limiting fixed point is still stable. So this is something that also needs to be taken into consideration. And then the analysis is similar outside of the parabolic punctures, but in this case, the space of local transformations, you don't need to require that these disks in the group land in the Borel. You just take the positive loop group. Okay, so that's the proof sketch, but maybe let me now in the remaining 4 minutes, 5 minutes, let me explain why these are just in case you haven't worked with Hecke modifications, why are these the correct spaces, or what is going on here? Okay, so rigorously what I've been saying about modifying our parabolic Higgs bundle around a puncture or around a point in general, not necessarily a parabolic puncture. Rigorously is just finding another parabolic Higgs bundle which is isomorphic in the complement of the point. So it only changes around the point. And so how you can do this? Let's take a parabolic puncture. So our point C, let's consider that it's in the divisor D. And then how you do it is you just look at it locally. So you fix a formal disk around the puncture, which we will call C1, and then the puncture disk, the intersection is going to be C01. And then if we forget about the Higgs field for a moment, the parabolic bundle is determined by its local data, by the data over C0, the restriction away from the point, then the restriction on the point, which actually because, the restriction to C1, so on the formal disk, and because it's a formal disk, we can trivialize, so we choose a trivialization here, and this, your bundle becomes a trivial bundle, and your parabolic structure becomes just whichever you want, the Borel, for example, the identity, and then a gluing function, okay? A gluing function over the puncture disk of the two PCs. And then this is equivalent to the starting thing by this Beauville-Laszlo theorem. And so now if you want to modify your bundle locally, the only thing you have to do is you take an automorphism of this trivial bundle over the puncture disk, and then you apply it before the gluing function. So you twist the gluing function. And so these automorphisms in the puncture disk of the group are precisely maps from the puncture disk to the group. So this is positive loop group. And then you have to take into consideration that if the automorphism lifts to an automorphism of the trivial bundle over the whole disk, not just the puncture disk, which is this Iwahori, it's the disks in the group which at the center land in the Borel so that they preserve the parabolic structure, then the result will be the same. So the natural space, after you fix the trivialization, the space of local transformations is this affine flag variety. And then we forgot about the Higgs field for a second. If we bring it back, the local expression, well, away from the point, we have this phi 0, which is a local expression. And then at the point, we have a map in the Lie algebra, which is comparable. So at the center of the disk, it has to lie in the Borel subalgebra. So we get an element of the Lie algebra version of the Iwahori subgroup. And then it has to be compatible with the gluing function. So if we twist the gluing function by sigma, by this sigma that we had before, we need to, and in the local expressions, we need to twist by sigma minus 1. Okay? And then we need to require that this lands in the space of compatible Higgs field, which is the Iwahori. Okay, and then as I was mentioning, there is a C-star action on this, which is induced from a principal co-character in the group, intertwining with the Hecke transformation. So yeah, just to finish, I want to say that, okay, now we have found these very stable upward flows. And then, of course, the next question which we want to work on is try to understand what the mirror BBB brain should be and how we can actually test this mirror. So once we conjecture what are the mirrors of this, which there are some conjectures in the geometric Langlands literature, I think. Then how can we test that these BBB brains are actually the mirrors? So yeah, this is the next step that we're trying to do. So thank you very much.
Okay, thank you very much. Are there any questions? Yeah, maybe a question is, can you use this to calculate sort of global examples?
In the sense as
Give some kind of description of like on P1 points.
Oh, right. Well, so you mean like computing explicitly for example, the upward flow, or what is the finite cover that you get, or something? Yeah. Yeah, actually, you can actually do that. At least I know how to do it when you just have this twisted divisor supported at one point, meaning that generically you have like a Hitching section, but then, or like like the fixed point in the Hitching section, but at a given point it's different. Then we can actually compute by applying a Hecke modification to the whole Hitching section, to every point in the Hitching section, we can get explicitly the upward flow and the finite cover. And then, as you mentioned, P1, there is also another example that we want to try, which is, Higgs points. So the moduli space of Higgs bundles on P1 with two punctures, and then maybe regular singularities in one of the punctures. And this should also allow to study kind of different sister actions where you also act on P1, and should give also more examples. Yeah.
Any further questions? Okay, so thank you, speaker again.